What does it mean when the ocean itself begins to erupt? What forces are capable of driving volcanic ash more than 13,000 feet into the atmosphere from a vent hidden beneath thousands of feet of seawater? And why do volcanologists pay such close attention when a submarine volcano suddenly shifts from silent hydrothermal venting into sustained ash-producing activity? Far from the coastlines most people associate with volcanic disasters, a powerful submarine volcanic system beneath the central Bismarck Sea near Papua New Guinea has entered what scientists consider a far more dangerous eruptive phase. Satellite instruments detected a rare volcanic ash emission beginning during the second week of May 2026, with ash columns rising to nearly 4 kilometers, or about 13,000 feet, above sea level. Satellite imagery also revealed widespread discoloration of seawater surrounding the eruption zone, one of the clearest indicators that magma, volcanic gases, and fragmented rock are now interacting violently with the ocean itself. This matters because submarine volcanoes do not normally produce sustained ash plumes visible high above the sea surface. Most eruptions occurring underwater are partially suppressed by hydrostatic pressure from the ocean above them. Water pressure acts like a giant lid on the volcanic conduit. At sufficient depth, expanding magmatic gases cannot freely decompress, limiting explosive fragmentation. In many submarine eruptions, lava simply extrudes quietly as pillow basalts or fragmented volcanic glass known as hyaloclastite. But when ash begins reaching the atmosphere, the physics of the eruption has fundamentally changed. The transition into an ash-producing phase usually means at least one of several important geological developments is underway. The eruptive vent may be migrating upward into shallower water where pressure is lower. Magma supply rates may be increasing fast enough to overcome seawater confinement. Gas content inside the magma may have risen dramatically, or the eruption may be entering a phreatomagmatic stage where seawater infiltrates the volcanic conduit and flashes into steam almost instantaneously. That last mechanism is one of the most violent processes in volcanology. When magma encounters seawater, the thermal contrast is extreme. Basaltic magma commonly erupts at temperatures near 2,100 degrees Fahrenheit, or roughly 1,150 degrees Celsius. Seawater in the deep Bismarck Sea may be only a few degrees above freezing. If seawater becomes trapped against magma and cannot escape quickly, it undergoes explosive expansion as liquid transforms into steam. Water increases its volume by roughly 1,700 times during vaporization. Inside confined volcanic conduits, that expansion can fragment magma into microscopic ash particles with tremendous efficiency. The result is not simply an underwater lava flow. It becomes a fuel-coolant interaction, a thermodynamic explosion driven by catastrophic heat transfer. This is why volcanologists become concerned when submarine volcanoes begin producing atmospheric ash emissions. Ash indicates intense fragmentation. Intense fragmentation indicates rapidly expanding gas phases, and rapidly expanding gas phases often mean the magmatic system is destabilizing. The volcanic province beneath the Bismarck Sea is already one of the most tectonically active regions on Earth. It exists within a highly complex convergent boundary where multiple microplates interact under enormous compressional stress. The region forms part of the broader Bismarck volcanic arc, generated primarily by subduction processes linked to the descent of the Solomon Sea Plate beneath surrounding tectonic blocks. Nearby volcanic systems across Papua New Guinea, including volcanoes such as Ulawun and Ritter Island, exist because oceanic lithosphere is continuously being forced downward into the mantle. As the descending slab sinks deeper, water-rich minerals inside the oceanic crust become unstable under rising temperatures and pressures. These minerals release volatiles into the overlying mantle wedge. The addition of water lowers the melting temperature of mantle rocks, generating magma through partial melting. Because molten rock is less dense than surrounding solid mantle, it begins rising upward through fractures and zones of structural weakness. But magma ascent is rarely smooth. As magma rises, dissolved gases begin separating from the melt. This process resembles carbon dioxide escaping from an open bottle of soda, except under vastly more extreme temperatures and pressures. Deep underground, volatile compounds such as water vapor, Carbon dioxide and sulfur dioxide remain dissolved because confining pressure is immense. But as magma approaches the surface, pressure decreases rapidly. Gas bubbles nucleate and expand. That expansion becomes the engine driving explosive volcanism. The viscosity of magma plays a critical role in determining whether gases escape gradually or become trapped. Low viscosity basaltic magma allows gases to escape relatively efficiently, often producing lava fountains or effusive eruptions. More silica-rich magma is stickier and more resistant to flow. Gases become trapped, pressure accumulates, and fragmentation becomes increasingly violent. Submarine systems complicate this process because seawater changes eruption dynamics completely. Hydrostatic pressure suppresses bubble growth at depth, meaning gases may remain compressed until magma rises into shallower water. Once pressure drops below critical thresholds, gas expansion can accelerate suddenly. The eruption can transition from relatively quiet extrusion into explosive decompression within a very short period. Satellite observations over the Bismarck Sea indicate precisely this kind of escalation may now be occurring. The ash plume detected by the Darwin Volcanic Ash Advisory Center rose several kilometers above sea level, while water discoloration persisted around the vent area. Water discoloration is more important than many people realize. Discolored seawater above submarine volcanoes often indicates enormous amounts of suspended volcanic material, hydrothermal precipitates, sulfur compounds, volcanic gases, and fragmented rock particles entering the water column. In some cases, the discoloration comes from finely fragmented volcanic glass. In others, it results from iron-rich hydrothermal fluids precipitating minerals as they cool in seawater. Sometimes floating pumice accumulates at the surface. Gas bubbling may also transport sediments upward from the seafloor. These plumes can extend across large distances depending on ocean currents and eruption intensity. Hydrothermal venting itself is common along submarine volcanic systems, but sustained ash emission into the atmosphere is comparatively rare. This distinction matters because hydrothermal systems and magmatic eruptive systems operate under different energy regimes. Hydrothermal activity is primarily driven by groundwater circulation. Seawater penetrates fractures within hot volcanic crust, becomes superheated, dissolves metals and minerals, then rises back toward the seafloor. This process can create mineral-rich plumes and seafloor vent ecosystems without necessarily indicating imminent eruption. Ash emission, however, means magma fragmentation is actively occurring. That fragmentation requires substantial internal energy release. It means the system has crossed a threshold where magma supply, volatile expansion, or magma-water interaction has intensified enough to eject material through the ocean and into the atmosphere. Submarine volcanic systems are especially dangerous scientifically because they are difficult to monitor directly. Unlike terrestrial volcanoes, where instruments can be installed around craters and lava domes, underwater systems are hidden beneath seawater that interferes with many conventional monitoring methods. Seismometers on nearby islands can detect earthquakes associated with magma movement, but locating precise vent activity beneath the seafloor is difficult. Satellite observations become critical because surface discoloration, thermal anomalies, floating pumice, and ash plumes may provide the first indications of escalating activity. The eruption dynamics themselves are also highly sensitive to water depth. At great depth, hydrostatic pressure suppresses explosive degassing. As a result, eruptions may produce bulbous pillow lavas formed when magma extrudes slowly into cold seawater. Rapid chilling creates glassy outer crusts while molten interiors continue flowing. If lava supply persists, the pillows accumulate into volcanic edifices. At intermediate depths, fragmentation becomes more efficient. Steam explosions intensify. Volcanic glass shatters into ash-sized particles. Pyroclastic material mixes with seawater to generate density currents moving downslope along the seafloor. At very shallow depths, submarine eruptions can evolve into Surtsian activity characterized by violent jets of steam, ash, and volcanic debris blasting above the ocean surface. These eruptions can eventually construct temporary volcanic islands if eruptive output exceeds wave erosion. The famous eruption of Hunga Tonga, Hunga Ha'apai, demonstrated how catastrophic such transitions can become. That eruption involved massive magma-water interaction and generated one of the most energetic volcanic explosions observed in modern times. The Bismarck Sea system has not approached that scale, but the geological mechanisms attracting scientific attention are related. Once submarine systems begin efficiently fragmenting magma, eruption intensity can escalate rapidly if conduit conditions continue evolving. One critical factor involves conduit permeability. Volcanic conduits are not simple pipes. They are dynamic fracture networks filled with magma, gas, fragmented rock, and hydrothermal fluids. As eruptions progress, conduit geometry changes continuously. Wall collapse can constrict pathways. Magma pulses may temporarily seal vents with solidifying material. Gas-rich magma batches may rise from deeper reservoirs. External seawater may infiltrate through fractures generated by volcanic earthquakes. These changes alter pressure distribution throughout the system. If permeability decreases, gases become trapped. Pressure rises. Fragmentation intensifies. Explosive pulses become more likely. This feedback cycle can transform relatively modest eruptive activity into sustained ash production. Another important process involves magma recharge from deeper reservoirs. Volcanic systems are rarely supplied by single static magma chambers. Instead, they often consist of vertically connected storage zones extending through the crust. Deep injections of hotter, volatile-rich magma can destabilize shallower reservoirs through thermal and mechanical interaction. When fresh magma enters an existing chamber, several destabilizing effects may occur simultaneously. Temperature rises reduce magma viscosity. Gas content increases. Convective overturn may develop inside the reservoir. Crystals formed during previous cooling episodes may partially remelt. Pressure within the chamber rises. Any combination of these mechanisms can initiate renewed eruptive activity. Volcanologists often watch for earthquake swarms preceding such transitions, because migrating magma fractures surrounding rock as it ascends. Earthquakes may propagate upward in patterns, revealing magma transport pathways. Harmonic tremor, a continuous seismic vibration associated with fluid movement, may also develop. Although detailed seismic data from the Bismarck Sea eruption remains limited publicly, the emergence of sustained ash emissions strongly suggests the magmatic system is now transferring energy more efficiently toward the surface. Submarine eruptions can also generate hazards beyond ash production itself. One major concern involves sector collapse and submarine landslides. Volcanic edifices constructed underwater are inherently unstable. They consist of fragmented volcanic debris, hydrothermally altered rock, and rapidly accumulated lava deposits resting on steep submarine slopes. Explosive eruptions weaken these structures further through fracturing and alteration. If part of the volcanic flank collapses suddenly, enormous volumes of material can accelerate downslope across the seafloor. These collapses may displace seawater and generate tsunamis. The Bismarck volcanic arc has a long history of catastrophic flank failure. The collapse of Ritter Island during the 19th century produced one of the deadliest volcanic tsunamis ever recorded. Much of the volcano failed catastrophically into the sea, generating waves that devastated nearby coastlines. Modern submarine eruptions raise concern, partly because scientists know how quickly volcanic edifices can destabilize once explosive activity accelerates. Another mechanism attracting attention involves volcanic gas release. Magma contains dissolved volatile compounds originating from mantle melting and crustal assimilation processes. During eruption, gases separate from the melt and escape into seawater and atmosphere. Sulfur dioxide, carbon dioxide, hydrogen sulfide, and halogen compounds are especially important. Sulfur dioxide emissions are commonly associated with magma ascent because sulfur exsolves efficiently during decompression. Once released into the atmosphere, sulfur dioxide can oxidize into sulfate aerosols capable of influencing atmospheric chemistry and radiative balance. Underwater, volcanic gas release alters seawater chemistry locally. Carbon dioxide can acidify surrounding water. Hydrothermal plumes transport dissolved metals. Reduced sulfur compounds support chemosynthetic biological communities around vent systems. Large gas releases may also contribute to buoyancy-driven water column disturbances. In extreme cases, rapidly ascending gas-rich plumes can decrease water density enough to disrupt local ocean circulation patterns. The interaction between magma and seawater also produces enormous quantities of volcanic glass. When magma cools rapidly underwater, crystal growth is suppressed because cooling rates exceed mineral nucleation timescales. Instead of forming coarse crystalline rock, the magma quenches into amorphous volcanic glass. Explosive fragmentation shatters this glass into fine ash particles. These particles behave differently from subaerial volcanic ash because seawater modifies aggregation processes. Ash grains may clump together through electrostatic interaction and salt precipitation. Density currents carrying ash can move along the seafloor, redistributing volcanic sediment across large submarine regions. Over geological time, repeated submarine eruptions build complex volcanic landscapes composed of overlapping lava flows, pyroclastic deposits, hydrothermal mineral accumulations, and collapse scars. The Bismarck Sea region represents one of the most active examples of this process on Earth. Its tectonic complexity arises because multiple small plates interact simultaneously rather than along a single simple plate boundary. Compression, extension, strike-slip deformation, and back-arc spreading all occur within relatively short distances. This creates numerous structural weaknesses through which magma can ascend. Back-arc tectonics are especially important here. In many subduction systems, extension develops behind the main volcanic arc as descending slabs roll backward into the mantle. This extension thins the crust and promotes decompression melting. Magma pathways become more numerous. Hydrothermal circulation intensifies. The result is a broad volcanic province containing both emergent volcanoes and submarine seamount systems. Submarine volcanoes in such regions often remain poorly mapped because detailed bathymetric surveys are expensive and technically difficult. Many eruptive systems are identified only after discolored water, pumice rafts, hydroacoustic signals, or satellite-detected ash plumes appear. That uncertainty increases scientific concern because baseline behavior is poorly constrained. Without long-term monitoring records, it becomes difficult to determine whether a volcanic system is undergoing ordinary episodic unrest or entering a much larger eruptive sequence. One reason ash emission from the Bismarck Sea eruption attracted immediate attention is precisely because such atmospheric ash production is relatively uncommon for deeply submerged systems. Ash reaching several kilometers into the atmosphere implies fragmentation energy sufficient to overcome seawater suppression. That usually indicates either shallow vent depth or increasing eruptive vigor. If the vent is becoming shallower through cone construction, eruption style may continue evolving. Repeated deposition of fragmented volcanic material can gradually build the volcanic edifice upward. As water depth decreases, hydrostatic suppression weakens further. Explosive magma-water interaction may intensify. This creates a potentially self-reinforcing cycle. Shallower depth increases explosivity. Increased explosivity produces more fragmented material. More fragmented material builds the cone upward faster. Further shoaling increases explosivity again. Some submarine eruptions eventually breach the ocean surface through this mechanism. But emergence does not necessarily stabilize the system. In fact, partially submerged eruptions can become even more explosive because seawater still accesses the vent intermittently while pressure suppression decreases dramatically. The physics of magma fragmentation under these conditions are extraordinarily efficient. Steam explosions can pulverize magma into ultrafine ash capable of rising high into the atmosphere and traveling large distances. Volcanic ash itself is not smoke. It consists of microscopic rock fragments, mineral crystals, and volcanic glass shards. Under magnification, ash particles often appear jagged and abrasive because they form through brittle fragmentation rather than combustion. This matters because airborne ash poses significant hazards to aviation. Jet engines ingest ash particles, which can melt within turbine sections and resolidify on engine components. The Darwin Volcanic Ash Advisory Center monitors eruptions in the region precisely because ash clouds threaten aircraft routes across the southwest Pacific. The detection of ash at 4 kilometers altitude indicates the eruption column possessed enough thermal buoyancy and momentum to penetrate well into the lower atmosphere. Eruption columns form because fragmented magma and volcanic gases are initially much hotter and less dense than surrounding air. As the mixture rises, entrainment pulls atmospheric air into the column. If thermal energy remains sufficient, the plume continues ascending until density equilibrium is reached. Even submarine eruptions can generate substantial atmospheric plumes once material breaches the sea surface. The ocean modifies eruption dynamics further through pressure oscillations generated by wave interaction. Surface waves periodically alter confining pressure at shallow vents. Though these pressure variations are relatively small compared to deep hydrostatic loads, they may influence gas release timing in marginally stable systems. Tidal forces may also modulate eruptive behavior slightly by changing confining stress conditions around volcanic conduits. Such interactions illustrate why volcanic systems behave as coupled thermodynamic and mechanical systems rather than isolated magma chambers. Every component influences the others. Magma ascent changes pressure fields. Pressure changes alter degassing efficiency. Degassing affects buoyancy and fragmentation. Fragmentation changes conduit permeability. Seawater infiltration modifies thermal transfer. Structural collapse reshapes vent geometry. The eruption becomes a constantly evolving feedback network. Scientists studying submarine volcanism increasingly rely on multidisciplinary monitoring to understand these transitions. Satellite thermal imaging detects heat anomalies. Synthetic aperture radar reveals ocean surface roughness changes from gas bubbling. Hydrophones record acoustic signals transmitted efficiently through seawater. Seafloor pressure sensors monitor tsunami-generating deformation. Geochemical sampling identifies volatile release patterns. Yet despite modern technology, submarine eruptions remain among the least understood volcanic phenomena on Earth. The seafloor hides most of the process from direct observation. That uncertainty is partly why rare ash-producing submarine eruptions generate intense scientific interest. They offer glimpses into magmatic systems normally concealed beneath the ocean. The current Bismarck Sea eruption appears to represent precisely such a transition. What began as submarine unrest has now entered a phase involving sustained ash emission, visible water discoloration, and evidence of vigorous magma-water interaction. Whether the eruption intensifies further depends on several evolving variables: magma supply rate, vent depth, conduit stability, volatile content, and seawater access to the eruptive system. If magma flux increases while the vent shoals further, explosive intensity could rise substantially. If conduit collapse seals gas escape pathways temporarily, pressure accumulation may produce larger explosive bursts. If the eruption instead stabilizes into open vent degassing, activity may gradually decline. At present, the geological significance lies not in confirmed catastrophe but in transition. The volcano has shifted from relatively concealed submarine activity into a more energetic eruptive state, capable of injecting ash directly into the atmosphere. That shift signals important changes within the magmatic plumbing system beneath the Bismarck Sea. And beneath the ocean surface, where tectonic plates continue grinding, fracturing, and melting deep within Earth's crust, those changes are rarely random. They are the visible surface expression of immense thermodynamic forces operating far below the seafloor, where magma reservoirs evolve under crushing pressure, volatile rich melts migrate upward through fractured crust, and the boundary between water and fire becomes violently unstable.